All right, 6.7, this is the one. This is the one where everybody says, when am I going to use this in real life? And I get to say, if you're going to be a scientist, this is the spot. Okay. Now, will you have to sit down and calculate all of these by hand every day? No. But you do need to understand how the equations are working, and that will help you to make an hypothesis, make estimations, do those kinds of things that are important to do and important to know how to do. Okay. All right, this section is going to be a lot of science-based stuff. So those of you that are not science people, don't panic. All you're really looking for is a couple of keywords. And if you can find the keywords, then you know where to plug the numbers in. And once you plug the numbers in, it's just another math problem that you punch in your calculator, okay? So, do you have to understand the laws of cooling and the laws of growth models and all of the half-life and carbon dating? No, you don't need to know all of that stuff, okay? If you're not a scientist, then focus on learning how to put in variables into certain calculators or into certain places to kind of determine what's going on, okay? Now, we can start a lot of times in the real world, we start with a set of data and then we have to work our way backwards. So this is just kind of this first exercise, just kind of an idea of what would that data look like and what does that tell me about what I should be looking for in terms of how is this going to act in the future? How did it act before this? Where is this information coming from? Can I turn it into a mathematical model? Okay, and then we will kind of continue this into 4.3 and 6.8, where we continue this idea of I'm going to take some data, and once I have data, what do I do with it? Okay, and as you go on to your stats classes, then you're going to do a lot of this again, and then go into, okay, now that I have the data and I turned it into a model, what does that tell me about everything else? Okay, so this is kind of your first foray into stats. Now this says enter the data into a graphing calculator. I don't have a calculator, and this particular app that I'm using to record the videos doesn't do really well if I switch to one. So I'm just going to sketch it real quick. I'm going to pause this, I'm going to sketch it, and then the sketch will appear in 3, 2, 1. So we've got data. Our data's plotted. This is called a scatter plot. Hopefully you've seen them before. They're not that weird. This one's a little rough. It's, it's a sketch. It's fine. But don't expect it to be too fancy because I'm still human. Okay, so we've got this sketch. And in this sketch, we have a lot of information. But mostly what it's asking is this data linear, exponential, or logarithmic? Well, if I can draw kind of a straight line and hit most of the data, which in this case I can, then we say this would probably be a linear model. Now, are you going to touch every dot along the way? No, but it's close. Okay. Now, if this was something that was exponential, then it would be data that kind of has an exponential growth pattern to it. We should expect it to kind of curve upward in one way or another. If it was data that was logarithmic, then we would expect our data to kind of have more of an upward curve like this. Okay, now you're just going to look at a scatter plot. You're going to take your numbers, you're going to plot them, you're going to look at that scatter plot, and it's going to tell you, oh yeah, that's logarithmic, or that I see a pattern and this is probably the shape of that pattern. Okay, so that's all that this type of question is going to ask. And we'll talk more about that when we do the little stats stuff kind of at the end of the class, just so you have an idea. Okay. Now, Newton's law of cooling. You have this temperature function. T sub t is a times e to the kt plus ts. Now, there's a lot of different numbers there. There's a lot of different variables there, okay? Capital T and lowercase t are two different variables. So this is one of those, well, in all of math, detail matters, and paying attention to the little details is going to be really important, okay? Capital T and lowercase t are very different, and we have to be very aware of that, okay? So capital T is the temperature at a given time. little t is the time since you made that first data recording, okay? A is the difference between the initial temperature and its surroundings. So like if the object you have is 90 degrees and you're in a 75-degree room, then your A value would be 15 because there is 15-degree difference in what you're looking at. Okay. K is a constant. This is a continuous rate of cooling for the object in question. K will almost always be given to you. Okay. It will be different if it's like soup versus if it's a pot you just pull out of a kiln. Okay, so there's a constant for each of these types of materials. And so once you have those materials kind of down, then you get that number. It will be given to you as part of what they're doing. Okay, so let's say the temperature of an object in degrees Fahrenheit after a certain amount of minutes is represented by the equation T sub T is 68 e to the negative 0.0174 T plus 72. To the nearest degree, what is the temperature of the object after 1.5 hours? Okay, now little t in this case should be measured in minutes. So 1.5 hours means that we're actually going to use 90. And then basically, all of these words are really just saying plug in 90, see what happens. Okay, so T sub 90 equals 68 e to the negative 0.0174 times 90 plus 72. Now be careful as you plug this in. And as you get better and better at using your calculator, it won't take you this many steps, but I want to show you step by step the order that it should go. Okay, so 68 times e, we're going to start by multiplying in the exponent. And we've got negative 1.323. So we're going to take e and we're going to raise it to that value. So now I've got 68 times 0.266335097. Then we multiply by 68. So I have 18.11078,659, and then add our 72 at the end. So the temperature after 90 minutes is going to be 90.11078,659. And then, it doesn't say, it doesn't give us, it says to the nearest degree. So we're going to round to the nearest degree. So after 90 minutes, we would expect this to be 90 degrees Fahrenheit. Okay, so just plugging in numbers to a given equation, being able to solve that down into something that means something to whoever's using it. Okay. All right, and then we're going to talk about a logistic growth model. This is a slightly different kind of model. It has to do with things that are limited in terms of growth. Okay, this is applied to most biological applications because if you're talking about, say, a population, the population of wolves in Yellowstone, they're not going to grow exponentially. Eventually, they're going to run out of food, or they're going to run out of space, or they're going to run out of other resources, right? If you're looking at bacteria in a petri dish, well, it's going to run out of space pretty quickly. Okay, so there's some sort of limiting factor where your population is going to begin growing exponentially, right? This first half is going to be an exponential growth. And then it's going to hit a point where from here on out, it's going to look more logarithmic. It's going to be more of a logarithm type thing, okay? It's never going to drop below 0, but it is going to have a limiting factor. And so we call this a logistic growth model. Okay, now you've got a lot of pieces in this. You have C, so whatever number is up here, this is the carrying capacity. That is how much that whatever that space it's in can use. It's the maximum amount that it can support. Okay, if you're looking at a petri dish of bacteria, it can only hold a petri dish worth of bacteria. So that would be the number of bacteria that can fit in a dish. Okay, the number of wolves that can survive in I don't know, given location. Okay. Now, if you want the initial value, you're going to have to do a little bit of algebra. You're going to take C over 1 plus A, do a little bit of arithmetic. That will tell you how many you started with. Okay. And then B is going to be a constant determined by the rate of growth. Again, just like with the K value, this one will usually be given. And it will depend on what you are growing. So, like the growth rate of the percentage of the United States with a cell phone is going to grow at a different rate than wolves in the wild, which is going to grow at a different rate than bacteria in a petri dish. So that is just your value, and for our class and our purposes, they're going to give us that number. Okay, so you don't usually have to worry about finding R. Okay, now in this one it's a 1 plus A, but we're just going to take whatever. So let's take our logistic growth model. F of x is 150 over 8 plus 8e to the negative 2x. Okay, so let's just look at what we have. So carrying capacity. According to the slide before this, carrying capacity is the number that's on top of that fraction. So our carrying capacity is 150. Easy peasy, right? Now our initial value is going to be 150 over whatever numbers are. So this is going to be 8 plus 8. So I have 150 over 16. And let me grab my calculator. That's going to give us 9.375. So whatever this model is modeling, I mean, we don't know what it is, okay? But it started with 9.375 of the things, okay? Now that's based on the previous slide. So let's look at f of 0. So 150 over 8 plus 8 times e to the negative 2 times 0, which is 0. So I have 8 plus 8, because e to the 0 is 1. And that ends up being exactly what we just found. Oops. 375. Okay, so f of 0 is 9.375, and that is also our initial value. Okay, so when you're looking for the initial value, you're looking for the y-intercept, and you're essentially plugging in x equals 0 exactly the same way we did at the very beginning of class. Okay. All right, f of 4. So I have 150 over 8 plus 8 times e to the negative 2 times 4. So this is 8 plus 8 times e to the negative 8. And then I'm just going to put that all into my calculator. Make sure that you do it carefully and that you're paying attention to where you put parentheses, etc., and that you're doing order of operations appropriately. Okay, you should end up with 16.5149. What does that mean? Okay, so I found it, but they want me to interpret it. So the interpretation here means at time 4, whatever that is, okay, we don't know if it's years, we don't know if it's decades, we don't know if it's minutes, okay, at time 4, there are 16.5149 things. Okay, and they didn't give us any context, so I can't be any more specific than that. So it could be after 4 minutes, there's 16 bacteria. It could be after 4 years, there's 16 of this animal in this area. Okay, so I don't know for sure, but I do know t is 4, so that's going to measure time, because little t means time, or sorry, x. I'm saying time the whole time, it's actually an x. But it's going to represent a time, so after that many time periods, I end up with 16 objects. Okay. All right, now I've got a frog farm, so I know what my objects are. Now they're frogs. T is time, and it's measured in years. So what is the initial frog population? Well, if it's my initial value, then T is 0. Okay, initial means that T is 0. So I've got 1,250 divided by 1 plus 9e to the negative 0.5 times 0. So I have 1250 over 1 plus 9, which is going to be 1250 divided by 10. So we started with 125 frogs. Okay, now just to kind of clarify some things or to add on to this, my carrying capacity is 1,250 frogs, because that was the number that was on top of the equation. So wherever they're in, whatever pond or facility or whatever environment they're in, it can only support 1,250 frogs. But the good news is they started with 125, and it took, probably going to take a while for them to get to that, a year or two before they max out. Okay. All right. An influenza epidemic spreads through a population rapidly at a rate that depends on two things. One, the more people who have the flu, the more rapidly it spreads. And the more uninfected people there are, the more rapidly it spreads. Okay? The two factors make the model a good one to study the spread of communicable diseases. So, now there is going to be a maximum value, right? Your carrying capacity is going to exist, and it's saying that your entire population is the carrying, right? I can't have more people with the flu than I have people, right? So I've got a carrying capacity, and it's everybody. So, for example, at time 0, there is one person in the community of 1,000 who has the flu. So in that community, at most 1,000 people can have the flu. Researchers find that for this particular strain of the flu, the growth constant is B equals 0.603. Okay? All right, so here we go. We're going to take our growth model, so our logistic growth model. Let's see, we're going to do f as a function of time. I'm just doing f for the flu. Okay, there's 1,000 people in my community, so that is my C value. This is 1 unless they tell me otherwise. I don't know what A is yet. And then E to the 0.603 T. Sorry, negative 0.063 T. I think I said it in my head, but I didn't write it down. Okay, now I need to get some values here. Okay, so step 1, I need to find A. Right? My initial value. And the only way to get A is that we know that our initial value is our carrying capacity over 1 plus A. I know 3 of those things. Okay. At time 0, there is one person. So initially, I have one person with the flu. I'm going to have up to 1,000, and then 1 plus A down here. Now, you can cross multiply. So 1 times 1 plus A equals 1 times 1,000, which means A is 999. Okay, so here's my model. Number of people with the flu is 1,000 over 1 plus 999 times e to the negative 0.603 t. Okay, now estimate the number of people in this community who will have had the flu after 10 days. Predict will have had the flu after a long period of time has passed. Okay, so that's two different questions. Okay, so 10 days. We're going to start with 10 days. So we're looking for f of 10. So I have 1,000 over 1 plus 999 e to the negative 0.603 times 10. And then we're going to take our calculator and we're going to type that in. And we end up with 293.85. Now, this is the number of people who either are currently, suffering from the flu or have had it and gotten better. Okay, so this is we're treating this like a cumulative number, not like at this moment in time 293 people have the flu. Okay, now we want this to make sense, so we're going to round this to the nearest whole number because you don't have 0.85 of a person. So we're going to make the estimation that after 10 days, 294 people have the flu. Okay, now predict how many people in this community will have had the flu after a long period of time. So as the days go on and on and on and on and on, and people interact with each other, and more people get the flu, eventually, after a long period of time, we should get closer and closer to that carrying capacity of 1,000 people. So after a long enough time, we would expect 1,000 people to have the flu, right? Assuming a lot of things, right? If this community is in a petri dish, no one leaves, no one goes anywhere else, no one comes in, right? Eventually, everyone in that community is going to get the flu, okay? All right, switching gears a little bit, chemical applications. A biologist recorded a count of 397 bacteria present in a culture after 5 minutes, 738 bacteria present after 15 minutes. To the nearest whole number, what was the initial population? Okay, so we have 2 points. We have a point at 5, where there were 397 bacteria. We have a point at 15, where there were 738 bacteria. And they want us to find the initial population. So we want to find where x equals 0. Well, to do that, I need a model. Now, I know that bacteria will grow exponentially. We're not working with logistic growth, okay? We've switched gears. We're out of logistic growth. We do not know if this is in a dish. Okay, and we also don't know how big the dish is. We don't know we don't know any of those things. So I can't apply a logistic model here because I don't have enough information. And when I don't have enough information, all I do know is that this is going to grow exponentially. And this is my exponential model. Okay, so we're going to go back to what we did at the beginning of chapter 6, and we're just going to come up with a model using 2 points. Okay, so 397 is a times b to the 5th. 738 is a times b to the 15th. I'm going to solve this for a. So a is 397 times b to the negative 5, or over b to the 5th. It's the same thing. So 738, instead of a here, I'm going to put 397b to the negative 5, and then times b to the 15 that was already there. So this is now a, and b is still there. And then I simplify. So b to the 10th equals 738 over 397. And you're going to turn this into a decimal for sure, because that just makes everything easier. So b is going to be the 10th root of 738 divided by 397. So b is 1.0639 6. When in doubt, use more decimal places than you think you need. Okay? And if that is B, then A is 397 times that number to the negative 5, which means A is 291.177. Okay. Now, if you remember, well, let me put this first. So our model is going to be 291.177 times 1.06396 to the x. Now, if you remember all the way back to the beginning of chapter 6, A represents your initial value. It's what we started with. So once I solve for A, I actually don't have to plug in 0. You can if you want to, but you don't have to. So it says to the nearest whole number. So we're going to take that 291.177. So our initial population for this process, we started with 291 bacteria. All right. Population of bacteria doubles every hour. If the culture started with 10 bacteria, graph the population as a function of time. Well, this is just an exercise in, do you understand what it means to double? Okay, so I'm going to start with 10 on the y-axis. So that's 10, 30, this will be 40, 60, 80, this is 100, 120, 140, 160. So my graph will go up to 180. On the x-axis, these are going to be hours. So this is 5 hours. And this is population on the y-axis. And I don't actually need anything past the first quadrant. Okay, so at 0 hours, I have 10 bacteria because that's what I start with. In 1 hour, that's going to double. So after hour 1, I've got 20 bacteria. In another hour, that's going to double again. So after 2 hours, I have 40 bacteria. Another hour, it's going to double again. So after 3 hours, now I have 80 bacteria. After 4 hours, I have 160 bacteria. And then my graph is going to run out. Okay, but I've got an exponential growth model. If I were to take, let's see, it's never going to go below 0, but it's going to go like this. And if I was going to go up to 5 hours, I would need to go up to 320 real quick. So that's going to shoot up real fast. Okay, so they just want you to recognize, again, from a different angle, what does it look like to have exponential growth? What does it look like to have an exponential model? All right, half-life. The half-life of a radioactive substance is 9.9 hours. What is our hourly decay rate? Okay, standard half-life formula. In this formula, A naught is your initial value. In this formula, it's a number, which means if I divide it out immediately, okay, so 1/2 A naught equals A naught e to the kt. If I just divide both sides by that number, then those kind of basically just go away. And I end up with half equals e to the kt. Okay, now there's some fancy solving here. What this question is asking me for is the hourly decay rate. So they want us to find k. So I'm going to solve this for k. So change it to a logarithm. So the natural log of 1/2 equals, I'm sorry, this should be negative kt. I did that That's a typo on my fault. Equals negative kt. We're going to divide by negative t. So k is negative natural log of 1/2 divided by t. Now in this case, t is 9.9 hours. So k is negative natural log of 1/2 divided by 9.9, which means k is going to be 0.07. Okay, that means this bacteria, or I'm sorry, not bacteria, this radioactive substance, probably some form of cesium, but you don't need to know that part either. Okay, this substance is decreasing by 7% every hour. Okay, your K value is a rate of decay. So you're decaying by about 7% every hour, which means after 9.9 hours, you're going to have half of what you started with in the beginning. And if you wait another 9.9 hours, you're going to have half of that new value, and then half of that new value, and half of that new value. Okay. All right, doubling time. Now I worked this formula out for you a second ago with half-life. It's the same idea with doubling time, right? I can take both of these, I can divide by a naught, and then change it to a logarithm and solve for t. And that's all they did here. Okay, so that's all that this kind of process is doing, is exactly what we did 2 slides ago. So very similar to half-life, except that we've got some issue, or some rewriting, and we've rewritten some things. So in this case, t is your doubling time. Okay, that's the important part to remember from this, and it is the natural log of 2 divided by k. Now I'm not sure if the k on the last slide should have been negative. I will look it up another day, or just double check it in your text. I probably have a typo on either this side or the last one. My guess is it's on the last one. All right. Research student working with a culture of bacteria that doubles in size every 20 minutes. The initial population count was 5 bacteria. What is the population size after 2.5 hours? Okay, so we're taking our population as a function of time, is our initial population times e to the kt, rounding to 4 decimal places. Now I don't know what k is yet. If this population doubles every 20 minutes, that means it doubles 3 times per hour. Okay, that means k is defined as doubling per hour. So 20 minutes happens 3 times in an hour, which means that k is 3. So now we are at the population is our initial population, which they said was 5 bacteria. We are doubling, which means instead of e, we're going to use a 2. And I know that's a little bit silly. I don't know why they explain it this way either. I just want to be consistent with what you're going to find in the written examples. Okay, so instead of using e, we're going to use a 2 because we know we're doubling. Okay, k is 3, and then we have our t, which in this case is in hours. So what is the population after 2.5 hours? So our population at 2.5 is going to be 5 times 2 to the 3 times 2.5, which is going to be 5 times 2 to the 7.5, and then 2 to the 7.5 is going to be 181 and some change, and multiply that by the initial 5, and we end up with the population after 2.5 hours is 905 and some decimals. Okay, but we're going to put that back into context and say after 2.5 hours, there are 905 bacteria. Okay, so again, it's just this section. You don't have to understand the science. They want you to put the science on the side and understand how to plug things into these equations, how to solve, how to turn them into numbers, and once you get those numbers, how to figure out what each one means. Okay.